Professor Dave here. Let's discuss basis and dimension.
He knows a lot about all kinds of stuff. Professor Dave explains.
We've gone over vector spaces and the spaces made from the span of vectors, as well as the linear independence of vectors. Now we want to combine all of this knowledge to form what is known as a basis. So let's learn exactly what this means. To put it as simply as possible, a basis is a set of linearly independent vectors that can be used as building blocks to make any other vector in the vector space. Written out, the vectors v1, v2, all the way to vn form a basis for the vector space V if and only if these vectors are linearly independent and the vectors span the space V. We've gone into detail about linear independence already, so here we can just focus on the part about span. This requirement says that the vectors v1, v2 to vn can be combined in some linear combination to express any other vector in the space V. Let's start with a simple example using the space of vectors of length 3, R3. Our vectors will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. To check to see if these vectors span R3, we must make sure a linear combination of them can equal any given vector of R3, which we will express as a vector composed of a set of scalars a, b, and c. Now let's check to see if a linear combination of our vectors can be used to equal this vector. It's important to remember that the scalars we multiply our vectors by, which are c1, c2, and c3, are the variables, while the a, b, and c that make up our given vector should be treated as regular numbers on the right-hand side of the equation. Writing this vector equation out as a system of equations, we get the straightforward result that c1 equals a, c2 equals b, and c3 equals c. Because we found a solution that's possible for any a, b, and c, these three vectors span the vector space R3. We can easily check that these three vectors are linearly independent by setting the right side equal to 0. So because a, b, and c equal 0, and as we saw, c1 equals a, c2 equals b, and c3 equals c, these scalars all end up being 0 as well. This was our condition for linear independence, and we have therefore satisfied the two conditions for these vectors to be considered a basis. They are the building blocks for any vector in R3, and because they are linearly independent, there is no extra information. We don't need any more vectors aside from these three, and if we take any away, we will no longer span all of R3. Now let's look at a more complicated example, the set of matrices in R2x2. We could check to make sure 4 matrices with a 1 in each corner is a basis, but let's instead consider the following 4 matrices. 1s on the top row with 0s on the bottom, then 1s on the bottom row with 0s on the top, then 1s on the diagonal with 0s for the other 2 entries, and then a 1 everywhere but the top left, which will be 0. First off, to check if these 4 matrices span R2x2, we will once again set a linear combination of them equal to any given 2x2 matrix, which we can generalize with the entries A, B, C, and D. So here we have each matrix being multiplied by its respective coefficient, and their sum equal to the generalized 2x2 matrix. We can distribute the scalars so that they show up as entries anywhere we had a 1 in a particular matrix, and then we can add up all the matrices to condense things a little bit, and we end up with this new matrix with sums in each of its entries. From here, we can write this out as a system of 4 equations. While we could solve this system of equations to try to find the solution, all we really have to do is make sure a solution exists at all. For a solution to exist, the determinant of the coefficient matrix must be non-zero, as we recall from learning Cramer's rule in a previous tutorial. So let's just set up the coefficient matrix, making sure to put zeros where the coefficients are missing in each equation, and then find the determinant of this 4 by 4 matrix, which won't be too difficult considering all the zeros. We end up getting a determinant of 1, which is indeed not 0, so a solution does exist to this system of equations, and our matrices can therefore be used to make up any 2 by 2 matrix. This means that our matrices span our 2 by 2. Next, we must check for linear independence. Let's take the same linear combination we just used and set it equal to a matrix full of zeros. We end up with the same equations as before, but with all the values on the right-hand side being equal to 0. We could solve these equations a few ways, but let's go ahead and use elementary row operations to get the coefficient matrix into row echelon form. We want the diagonal elements to be leading ones with all zeros below them. Let's start off by taking the second row and subtracting the first from it. Next, to get ones where we want them, let's switch rows 2 and 3. Now we can multiply the third row by -1 to get +1 here. Next, to get rid of this 1 in the second column of the fourth row, let's subtract the second row from the fourth row. And then we can get rid of this other 1 in the third column of the fourth row if we subtract the third row from the fourth. And this will leave us in row echelon form. We are left with no free variables in this form. All the diagonals have a leading 1. This means the only solution is all the scalars being equal to 0, which we could check by writing the matrix in equation form once again. Using this last equation, C4 must be equal to 0, and once we plug that into the equation above to get C3, and continue from there to get the other two, we end up with all 0 scalars. Thus, our matrices are linearly independent. We have verified both conditions for these matrices to be considered a basis for our 2 by 2. Before we wrap things up, we should go over one more definition. If a vector space V has a basis made of n elements, then the vector space is said to have dimension n. Taking our 2 examples from this lesson, we saw that R3 had a basis made of 3 vectors, and R2 by 2 had a basis made of 4 matrices. We can then say that R3 has dimension 3, and R2 by 2 has dimension 4. Beyond these examples, it is possible for vector spaces to be infinitely dimensional, and we also say that the set which contains only the 0 vector element has dimension 0. The dimension of a vector space is fixed, so no matter what basis we end up using for a vector space of dimension n, there will always be n elements in the basis, no more, no less. With vector spaces, subspaces and span, linear independence, as well as basis and dimension covered, we have established a lot of concepts and definitions that are important in linear algebra. This means we can now start expanding to more concrete operations. But first, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right, if we look at this, guys, here is going to be pretty much a general form for a conic, okay? So we can write all of our conic sections, a parabola, an ellipse, an hyperbola, a circle, all in this general form, all right? But we've also talked about standard forms, right? And I'm just going to go through one of them for each one, all right? And we'll kind of talk about it. So the first one we talked about was a parabola, where we said a parabola we could rewrite as x squared equaled 4p. Let's just do the x and k. That's fine. And actually, let's do, so x squared equals 4py. That is a parabola with the vertex at the origin, right? So that was a parabola. Then we talked about an ellipse. And remember, ellipse had x squared over a squared plus y squared over b squared equals 1. We had a hyperbola, which was, let's just do this, x squared over a squared minus y squared over b squared equals 1. And then we also talked about a circle, where a circle is going to be in a special type of ellipse, but a circle is when a and b are equal to each other. So we can just use a squared for each one. Now, ladies and gentlemen, for these three examples, all right, some of these are verticals. Actually, these are all have a horizontal, right? This is where, this one's going to be opening up and down. This one's where you're going to have a horizontal major axis. This will have a transverse axis, which is horizontal, and this one is just going to be a circle. So this is just a little general form when I talked about parabola, ellipse, hyperbola, and a circle. All right. Now, obviously, you guys know there's another type of equation, right? You can have the equation where the parabola opens horizontally. You could have a vertical major axis. Here, you could have a transverse axis, which is vertical, which would be the other formula. But the circle, we notice, is kind of always going to be the same. We always know that our A is going to equal each other, right? We know that these two have to be the same. You have the exact same major axis and minor axis. They're equal to each other. So if I gave you a formula in this, or if I gave you an equation that was in this formula, how could you determine if it was a parabola, an ellipse, hyperbola, or circle? You could convert it to each one of these formulas, right? Or their other counterparts. Or you can convert it to each one of these formulas and determine it. Or there's a little bit of a test that we can look at. All right. Now, so what we're going to do is, to do this test, we're going to look at the coefficients of our x squared and our y squared, right? So what you guys notice is that really our coefficient of x squared is 1 over a squared, right? And here for y is also going to be 1 over a squared. So if you kind of remember, what we can do is, if the coefficients of my x squared and my y squared are exactly the same, meaning if a is equal to c, then you know you're going to have a circle. So if you look in an equation and you know a is equal to c, then obviously you know that your major axis and your minor axis are the same. So if you have a equals c, that's going to tell you you have a circle when you have a conic section written in this format. Let's look at a parabola. On a parabola, we only have one squared, right? It's either x squared or y squared. In this case, I have an x squared. So therefore, I would have a 0 as the coefficient of y squared. So if I gave you a formula in this format, a or c, one of them would have to be 0, correct? Yes, John? Correct? Only one of them has to be 0 because there's only one x squared or one y squared. So if you were to multiply a times c and you got 0, then you know you have a parabola. So what I would look at, if you're given a formula in this form, if you only have one x squared or one y squared, ladies and gentlemen, then you know you're going to have a parabola. All right? Now let's go and take a look at an ellipse and a hyperbola. Notice, ladies and gentlemen, that an ellipse, we're always adding, right? We're adding our x squared over a, or we're adding the x squared and the y squared. So therefore, if I multiply a times c, that value has to be greater than 0, right? Two positive numbers are always going to add greater than 0. So if you multiply a times c and it's greater than 0, that value, so if you find your a and c and you add them up, you multiply them, and if it's greater than 0, then you have an ellipse. All right? Now, remember, hyperbolas was subtracting, right? It's the same thing, but now you subtract. So therefore, what you really have is a positive coefficient times a negative coefficient. That means if you have a times c is less than 0, then you have a hyperbola. All right, so these are going to be your main points you guys are going to want to know. So if I give you an equation in this format, all you need to do is understand if it's a times 0, then you have a equals 0. A times c equals 0, you have a parabola. A times c is greater than 0, you have an ellipse. A times c is less than 0, you have hyperbola. And if a is equal to c, then you know you have a circle when it's in this format. Okay? That's it. And guys, your
Trick to find dimensional formula. I will teach you the super easy trick to solve easy level and hard level questions. Firstly, I write here mass, length, time and current. We know that the SI unit of mass is kg, that of length is meter, that of time is second, and that of current is ampere. The dimensional symbol of mass is m, that of length is L, that of time is t, and that of current is A. Now consider this question. Find the dimensional formula of velocity. Well, we know that velocity is equal to displacement upon time. We know that displacement or length is the same thing. The dimensional symbol of length is L and that of time is t. Now I shift t from the denominator to numerator. I get square bracket L t to the power minus 1 square bracket. Or I write square bracket m to the power 0 L t to the power minus 1 square bracket. Remember that this m0 means that mass is not present in velocity. Hence the dimensional formula of velocity is m to the power 0 L t to the power minus 1. Secondly, find the dimensional formula of acceleration. Well, we know that acceleration is equal to change in velocity upon time. Now velocity is equal to displacement upon time, then this time. We know that dimensional symbol of displacement is L, that of time is t, and that of time is also t. I get L t to the power minus 2. Hence the dimensional formula of acceleration is Lt to the power negative 2. Thirdly, find the dimensional formula of force. Well, we know that force is equal to mass into acceleration. The dimensional symbol of mass is m, and we have already calculated the dimensional formula of acceleration, which is Lt to the power negative 2. I get m L t to the power negative 2. Hence the dimensional formula of force is m L t to the power negative 2. Note down all these dimensional formulas which I will directly use in hard level questions. Now consider these hard level questions. Find the dimensional formula of pressure, stress and modulus of elasticity. Well, we know that pressure is equal to force upon area, and that of stress is force upon area. Now I write force upon, we know that area is equal to length and to breadth. We have already calculated the dimensional formula of force, which is ml t to the power negative 2. The dimensional symbol of length and breadth is L and L. This L and this L squared cancel out. I get m L to the power negative 2 t to the power negative 2. Hence the dimensional formula of pressure and stress is square bracket m L to the power negative 2 t to the power negative 2 square bracket. In case of modulus of elasticity, its formula is equal to stress upon strain. We all know that strain is unitless. We get modulus of elasticity is equal to stress. We have already calculated the dimensional formula of stress, which is m L to the power negative 1 t to the power negative 2. Hence the dimensional formula of modulus of elasticity is m L to the power negative 1 t to the power negative 2. So these three physical quantities have the same dimensional formula. Thus note down all these dimensional formulas. Secondly, find the dimensional formula of work done, energy, torque and kinetic energy. Well, work done and energy are the same, are two faces of the same coin. We know that work done is equal to dot product of force and distance. We have already calculated the dimensional formula of force, which is mLt to the power negative 2, and the dimensional symbol of distance is L. I get mL to the power 2 t to the power negative 2. Hence the dimensional formula of work done and energy is square bracket m L to the power 2 t to the power negative 2 square bracket closed. In case of torque, it is the cross product of force and distance. The dimensional formula of force is m L t to the power negative 2 and that of distance is L. I get m L squared t to the power negative 2. Hence the dimensional formula of torque is mL squared t to the power negative 2. In case of kinetic energy, it is equal to half of mv squared. Remember that we do not consider constants in dimensional formula. The dimensional symbol of mass is m and the dimensional formula of velocity is Lt to the power negative 1. I take square root on it. I get mL squared t to the power negative 2. Hence the dimensional formula of kinetic energy is also mL squared t to the power negative 2. Thus remember that the dimensional formula of all these quantities is the same. So note it down. Finally, find the dimensional formula of resistance, reactance and impedance. Well, according to Ohm's law, V is equal to IR, or R is equal to V upon I. Let this is equation number 1. We know that voltage is equal to work done upon charge. Also we know that charge is equal to I upon time. So I write V is equal to work done upon charge into time. We already calculated the dimensional formula of work done, which is mL squared t to the power negative 2. The dimensional symbol of current I is A and that of time is t. I shift AT from the denominator to the numerator. I get mL squared t to the power negative 3 into A to the power negative A. Hence the dimensional formula of voltage is mL squared t to the power negative 3 A to the power negative 1. Let this is equation number 2. Now I plug in this equation number 2 and equation number 1. R is equal to the dimensional formula of voltage is mL squared t to the power negative 3 A to the power negative 1 upon the dimensional symbol of current is A. I get mL squared t to the power negative 3 A to the power negative 2. Hence the dimensional formula of resistance, reactance and impedance is mL squared t to the power negative 3 A to the power negative 2. Also remember that the dimensional formula of Boltzmann constant, entropy and heat capacity is mL squared t to the power negative 2 K to the power negative 1. While dimensional formula of angular velocity, frequency and angular frequency is m to the power 0 L to the power 0 t to the power negative 1. Thus note down all these important dimensional formulas which will help you in any exam. I hope that you have learned this super easy trick.
Hey everyone, welcome back to Wrath of Math. In today's video, we'll be answering the question, what is an ellipse? This is a viewer requested video. Always appreciate those requests. Be sure to leave yours down in the comments. With that said, let's start talking about this very cool shape, the ellipse. In this video, I just want to give you a good idea of what an ellipse is and introduce some related terms. There is a number of different ways that we could define an ellipse, but in this video, we'll be focusing on the definition that I think is most common, most intuitive, and to me, most interesting. Alright, that's enough dilly-dallying. Here is a beautiful example of an ellipse. An ellipse is defined by three things. The first two things are these 2 points. Each one of these points is called a focus of the ellipse. So together, they are the foci of the ellipse. That's the plural of focus. So again, an ellipse is defined by 3 things. The first 2 are the foci. We'll call this focus F1, and we'll call this focus F2. So what's the third thing we need to define an ellipse? The third thing that you need is a distance. Let's say that we pick a distance of 2a, and you'll see why we chose to write the distance as 2a instead of just a in a couple of minutes. But this is the third thing we need to define an ellipse, the distance. This 2a is just some number. Then what's important about this distance? What does it have to do with our ellipse? Well, let's say that we pick a random point on our ellipse. Let's say a point right there. Then we could consider the line segments from this point to the foci of the ellipse, these 2 line segments here. And let's just call this point P1. Alright, this is the part where we learn what's special about this distance. Let's say that we add the lengths of these 2 line segments. And we can write that like this. The magnitude of the line segment from P1 to F1, written like that. So that's the length of the segment P1, F1. And then to that, we're adding the length of the line segment from P1 to F2. So what do we get if we add the lengths of those 2 line segments? What we get is this distance that we chose, 2a. So given 2 foci and a distance, an ellipse is the set of all points such that for each point, the sum of its distances from each foci is equal to that original given distance. It's kind of similar to what a circle is. You might remember that a circle is a set of all points that have the same distance from a center. In an ellipse, the distance from any point to either of the 2 foci is not always the same, but if you add up those 2 distances from each foci, that sum will always be the same. So if this green point that I just drew is P2, then we could write that the length of the line segment P2F1 plus the length of the line segment P2F2 is, of course, equal to 2a. So pick any point you want on an ellipse. If you add up the distances from that point to the 2 foci of the ellipse, you'll always get the same number. And this isn't just similar to what a circle is, it's actually a generalization of circles. So a circle is actually a special kind of ellipse. A circle is an ellipse whose 2 foci are the exact same point. You can imagine that if we were to sort of squeeze this ellipse in at the sides until it resembled a circle, these foci would get closer and closer and then finally come together to make that one center of the circle. So a quick recap so far. What we need to define an ellipse is 2 points called the foci of the ellipse and a distance. Then the ellipse that information gives us is the set of all points, so that for each point, the sum of its distances from the 2 foci is equal to that original given distance. And a circle is a special type of ellipse. It's an ellipse whose foci are the same exact point. Alright, so that's the most important stuff out of the way. The most important thing about this lesson is that I want you to come away understanding what an ellipse is. But now let's talk a little bit about some important related terminology. Consider the line segment that passes through the foci of the ellipse and whose endpoints are both on the ellipse. This very special line segment is called the major axis of the ellipse. Something very cool about the major axis, guess what its length is? Its length, sure enough, is 2a, the original distance that we used to define the ellipse. And we can talk more about exactly why that's true another time, but it's certainly a beautiful property to keep in mind. Alright, now let's focus on the 2 foci of the ellipse again, pun completely intended. Consider the midpoint of the line segment connecting the 2 foci. That midpoint is about right there. So this point is equidistant from F1 and F2. But what's so cool about this point that we just drew? Well, this neat little point is called the center of the ellipse. And the center is also the midpoint of the major axis. So since these two distances are equal, and together they add up to 2a, we know that this distance is a, and this distance is a. Alright, that's neat, but another thing we can consider is the line segment, whose endpoints lie on the ellipse, is perpendicular to the major axis and passes through the center. That's going to be approximately this line segment right here. This line segment is perpendicular to the major axis, its endpoints lie on the ellipse, and it passes through the center. And this brown line segment is called the minor axis. The major axis of an ellipse is always greater than or equal to the minor axis in length. Of course, when the two are equal, what we're looking at is a circle. But if it's not a circle, then the major axis will be greater in length than the minor axis. Alright, there's really just two more quick things we've got to talk about. I'm going to clean up some of this stuff on the side so that we have a little bit more room to work with. Shrink this down, put it over there. If we just consider half of the major axis, we have a special name for this. This is called the semi-major axis. And remember that the semi-major axis, which is half of the major axis, has a length of a. That's half of the distance that we use to define the ellipse. And you might not be surprised to learn that we also have a special name for half of the minor axis. So if we consider this green segment here, this is called the semi-minor axis. The length of the semi-minor axis is usually represented by the variable b. These two measures, a, the length of the semi-major axis, and b, the length of the semi-minor axis, are used in a lot of calculations regarding ellipses, so that's why they are important. And so now you can see, by originally describing our distance as 2a, if we were to go on to write the equation of this ellipse or calculate its perimeter just for a couple of examples, we would get to use this nice variable a. Whereas if we had just defined the distance as d, then this would be 1/2 d, which doesn't look quite as nice. So just a quick recap of the second half of things we talked about. The center of an ellipse is the point that's halfway between the two foci. It's also the midpoint of the major axis, and I don't think I said this earlier, but it's also the midpoint of the minor axis. The major axis is the line segment that passes through the two foci and whose endpoints are both on the ellipse. The major axis has a length of 2a. Half of the major axis is called the semi-major axis and has a length of a. The line segment that is perpendicular to the major axis, that passes through the center of the ellipse, and whose endpoints lie on the ellipse, is called the minor axis of the ellipse. Half of the minor axis is called the semi-minor axis, whose length is usually denoted by the variable b. Those two lengths, a and b, are used in a lot of calculations regarding ellipses. And one last thing before we go, just wanted to show you an example of a tall and skinny ellipse, and here are its two foci. Alright, so that's just a whole bunch of stuff about ellipses. One of my old math teachers used to tell me that ovals don't exist, they're just ellipses. I always got a kick out of that. But anyways, I hope this video helped you understand what ellipses are. Let me know in the comments if you have any questions, need anything clarified, or have any other video requests. Thank you very much for watching, I'll see you next time, and be sure to subscribe for the swankiest math videos on the internet.
I can hear your voice from all the way up here, dear. Won't you please come to me? You love it up here, dear. There's a light where I float that erases all.
Imagine you're standing at one end of a large room and your friend is at the other end. You whisper something, barely audible to the person standing next to you. But your friend can clearly hear what you said. How amazing this would be, right? Is this possible? What do you think? Well, this magical thing is possible if the ceiling of the room is spherically shaped like an ellipse. This shape, which looks like a stretched circle, is what makes the whispering magic possible. If the ceiling of the room is elliptical in shape, technically semi-elliptical here, then there are two special points in the room where you and your friend can stand. If one of you whispers something, then all the sound waves get reflected from the elliptical ceiling towards the other person. So as the sound waves from one point get reflected and focused onto the other point, your friend can hear your whisper. This works the other way around as well. If your friend whispers something, you will be able to hear clearly as well. Based on this reflective property of ellipse, many rooms called whispering galleries have been constructed. For example, there's one at the Grand Central Terminal in New York City. Isn't this shape interesting? Each of these two special points of the ellipse is referred to as focus. And together, they're called the foci of the ellipse. Wait, there's more. Elliptical shapes even play a role in a medical device called the lithotripter. Due to its reflective property, it's used to break the kidney stones. High-frequency shock waves are generated at one focus of the elliptical-shaped reflector, which gets concentrated at another focus point where the kidney stones are positioned. And this helps in breaking the kidney stones. There is so much more that can be done with an elliptical shape. Can you explore other applications of this shape and tell us in the comment section below? In the next part, let's understand what exactly an ellipse is. How do we understand the shape of an ellipse? Suppose we have 2 points in a plane. We name this point as F1 and this point as F2. Now consider a special set of points on the same plane. They are placed such that their sum of the distances from these 2 points is constant. Let me explain. Suppose we take a point here. Let's name it A. Now let's say the sum of its distances from point F1 and point F2 is some number alpha. Now consider all such points whose sum of the distance from these 2 points is exactly equal to alpha. Are there any such points? Yes, there are many more. Collection of all such points is called an ellipse. Let's say we take a point B on the ellipse. Then the sum of its distances from the points F1 and F2 will be alpha. Let's take another point C here. Again, the sum of its distance from these 2 points will be alpha. So we see that the ellipse is a collection of all points in a plane such that their sum of distances from the 2 fixed points in the plane is constant. Each fixed point F1 and F2 is called the focus of the ellipse. And together they call the foci of the ellipse. Here we took the constant to be alpha, but we can take it any number for the constant sum of distances, with the only condition being that it should be greater than the distance between the foci of the ellipse. Now suppose we want the constant sum of distances to be beta. Let's say beta is greater than alpha. Then the set of points corresponding to this constant beta will be this ellipse. If we take the constant to be the number gamma, which is less than alpha, then the ellipse will look like this. Now let's look at one ellipse. An interesting thing happens when the 2 foci of the ellipse coincide. Can you guess? We get a circle. All the points will be at a distance of alpha over 2 from the center, where the 2 foci coincide. So we see that a circle is a special case of an ellipse when the 2 foci of ellipse coincide. So now we know that for an ellipse, we need to know 2 things. First is the 2 fixed points called the foci of the ellipse, and second, the constant sum of the distances of the points on the ellipse from these foci. Then the ellipse is the collection of all the points whose sum of the distances from the foci is that constant. Now many of you may have a question from our example of the whispering gallery. Suppose you and your friends are in a whispering gallery with an elliptical shaped ceiling. How will you know where to stand to hear the whispers of each other? That is where the foci of the elliptical ceiling are. For this, we need to delve a little deeper into understanding this shape. We will look at this in the next lesson. There we will understand some terminologies associated with the ellipse. Do subscribe to our channel to stay updated.
In this video, we're going to focus on ellipses. We're going to talk about how to graph an ellipse and also how to find the coordinates of the vertices and the foci of the ellipse. So let's begin. On the left, we have an ellipse with a horizontal major axis. On the right, the major axis is vertical. The length of the major axis is always equal to 2a. And that's the case for both types of ellipses. This is the length of the minor axis, which is vertical on the left, but it's horizontal on the right. The length of the minor axis, it's equal to 2b. For this one, the minor axis is horizontal, but it's still equal to 2b. Now, whenever you have an ellipse where it's centered at the origin, here's the equations that you're going to be dealing with. For a horizontal ellipse, it's x squared over a squared plus y squared over b squared. For the ellipse on the right, it's x squared over b squared plus y squared over a squared equals 1. Now, to determine which type of ellipse that you have, whether it's elongated in the x direction or elongated in the y direction, look at your a value. A is always bigger than b when dealing with ellipses. If the larger number is under x squared, you're dealing with an ellipse with a horizontal major axis. If the larger number a is under y squared, then the ellipse is vertical. It has a major vertical axis. So let's say this is the center. This is going to be positive a, or just a, and this is negative a, this is b, and this is negative b. So here are the major vertices, and these 2 points represent the minor vertices. For the graph on the right, here are the major vertices, and here are the minor vertices. For the ellipse on the left, the coordinates of the major vertices are plus or minus a, 0. For the minor vertices, it's 0, plus or minus b. For the ellipse on the right, it's the reverse. The coordinates of the major vertices are 0, plus or minus b, and for the minor vertices, it's plus or minus a, 0. Now let's talk about the coordinates of the foci. For the ellipse on the left, the foci will be along the major horizontal axis, and it's c units away from the origin or the center. So once you have the center, if you add c, you'll get the focus on the right. If you subtract it by c, you'll get the focus on the left. So the coordinates for the foci is going to be plus or minus c, 0 for the ellipse on the left side. For the ellipse on the right side, it's 0 plus or minus c. So starting from the center, you need to go up c units and down c units. And that will give you the coordinates of the foci. Now what happens if we have an ellipse that is not centered at the origin? If it's not centered at the origin, then the coordinates of the center become h, k. This equation changes to x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And the same is true for this equation. Everything will be the same, but we're going to replace x with x minus h squared. And this will be over b squared. And then we're going to replace y with y minus k squared. And this will be over a squared. Now let's focus our attention on the horizontal ellipse. When the center is the origin, I mentioned that the coordinates of the foci is plus or minus c comma 0. But now when the center is shifted to some point h comma k, the coordinates of the foci, or rather the foci, will be shifted. So all you need to do is add the coordinates of the center to the coordinates of the foci. So we're going to add plus or minus c to h. So it's going to be h plus or minus c, and then we're going to add k to 0, which will be k. So this will be the new coordinates of the foci for horizontal ellipse. Now the coordinates of the vertices are plus or minus a comma 0 and 0 plus or minus b. So when it's shifted, all you got to do is add the coordinates of the center to the vertices to get the new one. So to get the major vertices, it's going to be h plus or minus a comma k, and for the minor vertices, it's going to be h comma k plus or minus b. Now let's consider the situation if we have a vertical ellipse. As the center shifts from the origin to some point h comma k, let's see what's going to happen to the foci. So the coordinates of the foci, if the center is at the origin, is 0 plus or minus c. When the graph has shifted from the origin, it's going to be h comma k plus or minus c. The major vertices will be 0 plus or minus a. The minor vertices is plus or minus b comma 0. So when it's been shifted, this becomes h comma k plus or minus a, and this becomes h plus or minus b comma k. Now let's work on some practice problems. Go ahead and graph the ellipse and identify the coordinates of the vertices and the foci. By the way, in order to find the foci, you need to know how to calculate c. And here is the equation to calculate c. It's a squared minus b squared. Well, c squared is a squared minus b squared, not a squared plus b squared as in the case of the Pythagorean theorem. For hyperbolas, it's c squared equals a squared plus b squared. But for ellipses, c squared is equal to a squared minus b squared. So that's how you can calculate c, using that formula. So feel free to try this problem. In this problem, there's no h or k value. So the coordinates of the center is 0, 0. A squared is going to be the larger of the two numbers. So 9 is greater than 4. That means a squared is 9, which means a is the square root of 9. So a is 3. B squared is the other number, 4, which means b is the square root of 4, or 2. So now that we know the values of a and b and the center, we can go ahead and graph the ellipse. So first, let's plot the center. A is under the x variable, so we're going to travel 3 units to the right from the center along the x-axis and 3 units to the left. So this gives us the coordinates of the major vertices, which is going to be plus or minus a comma 0 or plus or minus 3 comma 0. Now b is 2, and b, or b squared, is under y squared. So we're going to go up 2 units from the center along the y-axis and down 2 units. So this gives us the coordinates of the minor vertices, which is 0 plus or minus b, or 0 plus or minus 2. So those are the coordinates of the vertices of the ellipse. Now we can go ahead and graph the ellipse by connecting these 4 vertices together. So that's how you can graph an ellipse. Now how can we find the coordinates of the foci? So the coordinates of the foci is going to be plus or minus c, 0. It's going to be along the major horizontal axis for this problem. So since A is along the x-axis, the foci will be along the x-axis as well. So we need to determine c. We know that c squared is a squared minus b squared. A squared is 9, b squared is 4. 9 minus 4 is 5. Taking the square root of both sides, we get that c is equal to plus or minus the square root of 5. So the coordinates of the foci will be plus or minus root 5, 0. If you have your calculator and you type in the square root of 5, the square root of 5 is 2.236 approximately. So along the x-axis, that's going to be somewhere in this region. So that's how we can plot the coordinates of the foci for this problem. Now let's try a similar problem to the last one. So for the sake of practice, feel free to pause the video and work on this example problem. Go ahead and graph the ellipse and then find the coordinates of the vertices and the foci. So the first thing we should do is identify the coordinates of the center. There's no h or k for this problem, so the center is going to be the origin. It's 0, 0. Next, we need to determine our a squared value. Is it 9 or is it 16? A squared will be the larger of the two numbers. 16 is greater than 9, so a squared is 16. So once we have a squared, we need to calculate a. A is going to be the square root of 16, which is 4. B squared has to be the other number, 9. Thus b is going to be the square root of 9, which is 3. So now that we have a and b, we can go ahead and graph the ellipse. So b is 3, and b squared is associated with the x variable. It's under x squared. So what we're going to do is we're going to travel 3 units to the right from the center and 3 units to the left from the center. So this is going to give us not the major vertices, but the minor vertices. The minor vertices is always associated with b. So the coordinates of the minor vertices for this problem is plus or minus b, 0. So that's plus or minus 3, 0. Now a is 4, and it's associated with y. A squared is under y squared, so a is going to be along the y-axis. So we're going to travel 4 units from the center and 4 units below the center. So the coordinates of the major vertices will be 0, 4 and 0, -4. And here's the center. So it's 0 plus or minus a, or 0 plus or minus 0, plus or minus 4. So now let's go ahead and graph the ellipse. So that's how we can plot it. Now the last thing we need to do is find the coordinates of the foci. So because the major horizontal axis is the y-axis in this case, the foci will be along that major vertical axis. But first we need to calculate c. Let's use this formula. C squared is equal to a squared minus b squared. A squared is 16, b squared is 9. 16 minus 9 is 7. So c is going to be plus or minus square root 7. Now the square root of 7, it's about 2.2 6. So the coordinates of the foci will be in this region. It's in the same direction as plus or minus a, which is along the y-axis. Now the coordinates of the foci in this problem is going to be 0, comma, plus or minus c, or 0, comma, plus or minus the square root of 7. So that's how you could find the coordinates of the foci, as well as the coordinates of the vertices. Number 3, identify the coordinates of the center, vertices, and foci, and then graph the ellipse. So the center is going to be h, comma, k. Here we have x minus 3. H is simply going to be 3. You just need to change the sign. Here we have y plus 2, so h is going to be, k is going to be negative 2. So that's h and k in this problem. So now that we have the coordinates of the center, let's determine our a and b values. So which one is going to be a squared, 16 or 25? Well, 25 is larger than 16, so a squared will be 25. A is going to be the square root of 25, which is 5. B squared is the other number, 16. So B is going to be 4. Now let's go ahead and graph it. So first, let's plot the center, which is 3, negative 2. So we're going to travel 3 units to the right, and we're going to travel down 2 units. So there is the center. Now, a is 5, and a is associated with the y variable. So from the center, we're going to go up 5 units. Right now, we're at a y value of negative 2, so we're going to stop at 3. And then we're going to go down 5 units. And so the coordinates of the vertices, rather than being 0, comma, plus or minus a, it's h, comma, k, plus or minus a. H is 3, k is negative 2, a is 5. Negative 2 plus 5 is 3, and negative 2 minus 5 is negative 7. So here, this point is at 3, comma 3, and this point here is 3 and negative 7. So those are the coordinates of the major vertices. Now, let's focus on B. B is 4, and it's associated with the x variable, so we're going to go 4 units to the left and 4 units to the right, starting from the center. So let's go 4 units to the right. So we get this point here, and then 4 units to the left will take us to this point. So the coordinates of the minor vertices, rather than being plus or minus b, comma 0, it's going to be h plus or minus b, comma k. H is 3, b is 4, k is negative 2. 3 plus 4 is 7, and 3 minus 4 is negative 1. So this point here, that's 7, negative 2, and then this other one is negative 1, negative 2. So now let's go ahead and graph the ellipse. So that's how we can graph this particular ellipse. And we have the coordinates of the major and minor vertices. Now, let's focus on finding the coordinates of the foci. So the major axis left, or the major axis is vertical. Thus, the coordinates of the foci will be along that line. So rather than being 0, plus or minus c, it's going to be h, k plus or minus c. So let's begin by finding c. C squared is going to be a squared minus b squared. A squared is 25, b squared is 16. 25 minus 16 is 9. The square root of 9 is 3. So c is going to be plus or minus 3. By the way, technically, a is plus or minus 5, and b is plus or minus 4. Because to get the coordinates of the vertices, we would have to add 5 and subtract 5 from the center. So it's technically more accurate to say plus or minus 4 and plus or minus 5 for a and b. So now that we have the value of c, we said that c is plus or minus 3. Let's use this to find the coordinates of the foci. So h is 3, k is negative 2, and we're going to add plus or minus 3 to that. Negative 2 plus 3 is 1, and negative 2 minus 3 is negative 5. So we have a focus at 3, 1, which is here, and we have another one at 3, negative 5, which is here. So technically what we need to do is, starting from the center, we would go up c units, or up 3 units, to get this point, 3, 1, and then we would travel down 3 units to get the other focus, which is 3, negative 5. Number 4, identify the coordinates of the center, vertices, and foci. And then we'll graph the ellipse. So let's begin with the center. So here we have a negative 1 in front of x. We're going to change it to positive 1. And here we have a positive 1 in front of y. So this will become negative 1. So the center is at 1, negative 1. A squared is going to be the larger of the two numbers. So a squared is 9. A is going to be the square root of 9, which is 3. If you want to write plus or minus 3, that's up to you, but if you just put 3, you can still graph it correctly, and you'll still get the correct coordinates. B squared, that's going to be 4. The square root of 4 is 2. Now let's go ahead and calculate c. So c squared is a squared minus b squared. A squared is 9, b squared is 4. So c squared is 5. The c is going to be the square root of 5. And you could write that as plus or minus root 5 if you want to. Now let's go ahead and graph the ellipse. Let's first put the appropriate markings on the x and y axis. So the center is at 1, negative 1, which is here. A is 3, and A is associated with the x variable. So we're going to travel 3 units to the right and 3 units to the left. B is 2, and it's b squared is under y squared, so we're going to go up 2, parallel to the y-axis, and then down 2. So that's how we can graph the ellipse in this problem. Now let's identify the coordinates of the vertices. If you ever forget the formula, you can just look at your graph. So here we can see that it's 4, negative 1, and here the x value is negative 2 with the y value is negative 1. So it's negative 2, 1. And if you remember the formula, it's h plus or minus a, k for a horizontal ellipse. H is 1, A is 3, k is negative 1. So you get 1 plus 3, which is 4, and 1 minus 3, which is negative 2. And this should be negative 2, negative 1. So those are the ways in which you can find the vertices of the ellipse. Now let's find the minor vertices of the ellipse. So this point here has an x and y value of 1, and this point here has an x value of 1 but a y value of negative 3. Or you could use this formula. It's h plus or minus b. Actually, I take that back. It's h comma k plus or minus b. So h is 1, k is negative 1, b is 2. So it's negative 1 plus 2, which is 1, and then it's negative 1 minus 2, which is negative 3, giving us those two minor vertices. I want you to be familiar with this formula because sometimes a or b could be a radical value. And to get the right answer, you need to use that formula, as will be the case of the foci in this example. So the coordinates of the foci for horizontal ellipse is going to be h plus or minus c comma k. H is 1, c is the square root of 5, so it's going to be 1 plus or minus root 5 comma k. In this case, we can't simplify the coordinates of the foci. So we have to leave it like this. So that's our answer for the coordinates of the foci. So starting from the center, we would have to travel c units to the right. The square root of 5 is like 2.2 something, 2.236. So going a little bit more than 2 to the right would take us somewhere to this point, and a little bit more than 2 to the left will take us to that point. So that's approximately where the two focal points will be. But this is what you would report as your answer for the coordinates of the foci. So anytime you have a radical, it's going to be hard to identify the points using the graph. You need to use this expression. So that's why I want you to learn how to use it, because you're going to need it for some problems. Number 5. Write the standard form of the equation for the ellipse shown below. So first, we need to realize that the center is at the origin. And this is a horizontal ellipse, where we have a horizontal major axis. So a squared is going to be under x squared. So this is the general formula of the equation that we need to use. X squared over a squared plus y squared over b squared is equal to 1. So if we could find the values of a and b, we could write the equation in standard form. A is 4, because this point here, the major vertices, is 4 units away from the center. We can see that b is 2. The minor vertices are 2 units away from the center. So if a is 4, that means that a squared is 4 squared, which is 16. And if b is 2, b squared, or 2 squared, is 4. So the formula that we have is x squared over 16 squared plus y squared over 4 squared is equal to 1. So this is the answer for this problem. Number 6. Write the standard form of the equation for the ellipse shown below. So we're given the center of the ellipse, which is -3, 2. And we could find a and b. So the distance between the center and one of the vertices, we could see it's 1, 2, 3, 4, 5 units. So it's 5 units along the x direction, and along the y direction, it's 1, 2, 3. Let me use a different color to count. So this is 1, 2, 3, 4. So we went down 4 units to get one of the minor vertices. So a is going to be the bigger number. That means a is 5, b is 4. If a is 5, a squared is going to be 25. B squared is 16. So now that we have the values of a squared and b squared, and we have c, our center, we can write the standard form of the equation. So a is horizontal. So what we have is a horizontal ellipse, or an ellipse with a horizontal major axis. So the formula we're going to use is x minus h squared over a squared, since a is parallel to the x-axis, plus y minus k squared over b squared is equal to 1. H is -3, k is 2. So this is going to be x minus h. Let's use brackets for now. H is -3. A squared is 25. And then y minus k is +2. B squared is 16. So this becomes x plus 3. So we change -3 to +3. Squared over 25 plus y minus 2 squared over 16 is equal to 1. So that's how we can convert from the graph to the equation in standard form.